Okay, hello everyone. In this video, I'm going to show you how the shear moment diagram. Okay, so what's the shear moment diagram? Actually, shear moment diagram it just give you a complete pictures how what kind of the pictures show the internal or external is force acting in the beam or on the beam. Okay, so because I remember so in previously when we tried to calculate stress, bending stress, and bending stress and transverse shear in beam. Do you remember the formula? Okay, do you remember the formula? Okay, for the bending stress is my over I. Okay, and the transverse shear is VQ over IT, right? Okay, so actually, in this two formula, actually, there is important physical quantity. And for the shear bending stress, okay, we need to know the moment. Okay, and for transverse shear, we need the shear force. So actually, the shear moment diagram is helping you to determine the moment and moment the moment bending moment and shear force at a particular cross section. Okay, so that's why we need a so-called shear moment diagram. Okay, also okay, and in this problem, I'm going to show you the simplest example for shear moment diagram. We start from very simple one first. Okay, okay, and at the beginning of drawing shear moment diagram, so you need to do the rigid body equilibrium. Yeah, again. Okay, so rigid body equilibrium. Don't forget rigid body equilibrium. Rigid body equilibrium is the heart of this course. Okay, and okay, let's look at a problem. This is a beam. Okay, and A is a pin support, and B is a roller support. Okay, do you remember what support? I think in the first half of the semester we introduced pin support, and B is a roller support. Okay, and the support has a reaction force and reaction moment, right? Okay, and for the pin support is only has a reaction. So let's draw a free body diagram of this beam. Okay, it says 30 kilonewton here acting on here, and the pin support only have the reaction. We only had reaction force, and the pin support you have reaction force point up and point right. Okay, I also assume everything is positive. So that's AY, that's AY, and this AX. Okay, AX. And for the rotor support, we only have this reaction force, so it's BY. Okay, so before you draw the shear moment diagram, you need to solve the reaction force or reaction moment using rigid body equilibrium. Okay, so don't forget rigid body equilibrium. And in this problem, okay, we only have force on vertical direction, so the AX must be zero. Okay, actually X also must be zero. Okay. Okay, in this problem, we only have the vertical force, vertical component force. So AX equal to zero. Okay, and so let's see. Okay, so we have AY point up, BY point up. So AY plus BY and minus 30 because this 30 kilonewton point down. So minus 30 equal to zero. So we have AY plus BY equal to 30. And right now we cannot solve the AY and BY, okay, because we only have one equation. So do you have another equation? Yes, we can have another equation. If we use A as the reference point, let's use summation MA equal to zero. So we are 30 kilonewton point down, and the distance here is 2, and here is force. So the moment A is a reference point, so this force will create a clockwise rotation. So clockwise, so that means negative, so minus 30 times 2. And plus, this is a by, and this will create a counterclockwise rotation. So plus by times 6 is equal to 0. Okay, so you can, by using this, you can solve the by very easily, okay? So you will find by is 10 and unit is kilonewton. So we have by equal 10. So that means the ay is 20, right? So we have ay is equal to 20 and the by is equal to 10. Okay. Okay, so that's the reaction force we have solved. Okay, and then after we solve the reaction force, we can start to draw in the shear moment diagram. Okay, so actually it's just drawing the shear force. Actually, shear force is just the force you just solve. Okay, for A, Y, and B. This is just shear force because we push down on the beam. If, for example, you push down at the beam, you create a shear force. You create a shear force in the beam. Yeah, remember that? You push it down the force and create a shear force, internal shear force in the beam. Okay, and okay, okay, okay. So just stop here. Okay, so let me draw this. Okay, so shear moment diagram. So here I think it's V, and what unit we are going to use? We use kilonewton. Okay, we use kilonewton. Okay. Okay, so the kilonewton. So we start in draw from A. Okay, A the reaction force like external, actually the shear moment diagram. Actually the shear force is external. Okay, external shear. Okay, external shear is just a reaction shear for just the force. It's just the reaction force you just solve. Okay, so the AY is 20. So AY, let's say 20. So we say 20 is here, 20 kilonewton. Okay. So between 0 to 2. Okay, between 0 to 2, maybe 2 is here. Between 0 to 2, there is no external loading between 0 to 2. So this shear force is the same. Okay, it's the same. It's keep at 20. Okay. Okay, but at this position, x equal to, okay, I may call this here x. X equal to, there's a 30 kilonewton point down. Okay, so here is 20. So you have a 30 kilonewton point down. So that would makes your shear force from 20 and minus 30. So it will become here. So I will draw this down. Okay, he will make you become here is minus 10. Okay, because as position 2 here, 2m here, there is an external 30 kilonewton point down. So the shear will make you the shear force here 20 and minus 30. So it could become minus 10. So the force will become here. Okay. Okay, so and between the 2 and the 6, okay, between 2 and 6, there is no other external force here. So it will keep a straight line here. Okay, but at the final point, at the final point, be here, end the point here. Okay, he will back to 10, back to 0. Back to 0. He will back to 0. Okay, so I think we should draw like this. He will back to 0. Okay, it must back to 0. Or if it doesn't back to 0, that means you are not in rich body equilibrium. It must back to the 0. Okay, back to 0 is here. So actually you just saw the reaction force at the B. Sorry, the reaction force at the B is 10, right? Yeah, your minus 10 goes to the end point, and then you plus this force plus 10. So it's minus 10. Okay, the reaction force here at the B is 10. So minus 10 plus 10, so it back to a 0. Okay, so it must back to 0. Okay, so that's the shear force diagram of this beam. Okay, let's just shear. Okay, right now next is a moment. And typically the shear moment diagram is drawn in vertical fashion, but right now I don't have the I don't have space, so I just draw in parallel fraction. Actually, I draw vertical They should draw in vertical fashion. Okay, so just start from here. Uh, yeah, maybe I didn't draw it very beautifully. Uh, So, okay, let's start this moment. Okay, what's the unit with kilonewton times the meter? Okay, we use kilonewton times meter. That's much easier. Okay, so how to draw the moment diagram along in x direction? So you need to know this. At the previous slide, we say after there's some theoretical derivation. If you are interested in the theoretical derivation, you just look at the slide, okay, by yourself. Okay, the moment. Sorry. The how to draw the moment. Okay, you must know this. Change in the moment equal to the area under the shear diagram. Change in the moment equal to the area under the shear diagram. Okay, so let's take a note of this. Okay, change in moment. Okay, change in moment. Change. Okay, so okay, I'll say moment change. Okay, moment change equal to area under the shear curve. Changing moment change equal to the area under the shear curve. What does that mean? Okay, let's start to do a shear not this moment diagram. Okay, because A, there is no moment. Okay, there is no moment at A, so we start from zero. We start from zero. Okay, because there is a moment at A. Okay, there is only reaction force. There is no reaction moment. Okay, at A. Okay, so we see moment change equal to the area under the shear curve. Let's back to this shear curve. Okay, from 0 to 2, what is the area here? Its area is equal to 20 times 2. Okay, 20 times 2. So it's 40. So that means between 0 to 2, the change of the moment is equal to 40. You see? Uh, okay, between 0 to 2, the moment change equal to the area under the shear curve. So between 0 to 2, the change of moment is 20 times 2, so it's 40. And at the beginning, we have 0, right? So the change is 40, and most importantly, it's positive. Okay, 20 times 2 is positive. So that means between 0 to 2, the change of moment is 40 and it's positive, and we start from 0. So at this point, it will become 40. Okay. Okay. So, okay, and the next question is between 0 to 2. Okay, we know it's 0 from 40, and it's steady increase or gradually decrease, or initially very slow and then increase finally. Which one? Which one? Because we know it changed from 0 to 40. Yeah, it's gradually decrease. Okay, it's this kind of increase or this kind of increase or steady increase. Okay, so how to determine which line? So you need to know this. You need to know your shear force diagram. Let's see if we slice this area. Okay, you see this slice. We slide this area. You see each area is the same. Okay, you see each area is the same. Each area, if we slice this area, you will see the change of the slice is steady. Okay, the change is okay. The change is a constant. A change is a constant. If we slice this area, maybe I draw here. If we slice this rectangular here, you see the change is steady. Okay, maybe I'm right, then doesn't draw it very good. Okay, okay, the area is steady. So the area is steady. The area is steady. STEA. Oh, I should say that the area is constant. Okay, the area is constant. And the area is constant means this each slice, the area is the same. Each slide area, each tiny area is the same. Each tiny area is the same because we have the same height, and if we have the same dx, this is all dx. This is all dx. We have the same height and we have the same dx, so the area is constant. Okay, so and then back to this description. The moment change equal to the area under the shear curve. Okay, if the area, if each small area is the same, that means the moment change is constant. If the slight area is a constant, that means the moment change is constant. The moment change is constant. Okay, let's tell you that. So that means, okay, so here is a logic. Yeah, you really need to know the logic here. The logic is here. Okay, we have the same slight area. That means the same tiny area. So the tiny area is a constant. Okay, that means the moment change is constant. Moment change is constant. Okay, and what is the moment change? Okay, what is the moment change? It's dm over dx. Okay, so that means the slope is constant. Okay, so from 0 to 40, slope is constant, so it is this curve. Okay, follow the logic, understand the logic. Okay, this is called so-called graphical method to draw the shear moment diagram. This is called graphical method. Yeah, there's another method using mathematical way to draw the shear moment diagram. But if you using mathematics to draw shear moment diagram, that will create more that will increase the difficulty to draw a diagram. So in this course, I show you this method, so-called graphical method to draw the shear moment diagram, because I think it's much easier to do. Okay, compared to using the mathematical formula to draw the shear moment diagram. Okay. Okay, so the tiny area is the same. Okay, that means the moment change is a constant. Okay, the tiny area is constant. That means the moment change is a constant. The moment change is dm over dx is constant. That means slope is constant. So it will look like the curve will look like this. So it's true. So between 0 to 2, the moment change from 0 to 40. Okay. Okay, and the next thing is very interesting. Okay, so we have the other half part. Yeah, half part is 2 to 6. 2 to 6. Okay, keep in mind, change of the moment equal to area under the shear curve. Let's go back to this curve, area, this area under the shear the area under this curve. Okay, so between 2 and 6. Okay, here is 4, and here is 10, and it's minus 10. So the area of this curve, well, you have to consider positive, negative, okay, because it's very important. Very important. You have to consider negative, positive, and negative. So it's minus 10 here, and here is a 40. So it's minus 10 times the 40. So it's minus 40. So let's tell you between 2 and 6, the change of the moment change is equal to the area under this curve between 2 and 6. Between 2 and 6, the area now is minus 40. That means the change of the moment is minus 40. So it's minus 40. Let's look at the moment at the position x equal 2. At x equal 2, the moment is 40. And it tells you between 2 and 6, the change of moment is minus 40. That means after from 2 to 6, the moment will change from 40 to 40 minus 40. So it will become 0. Okay. So it will become 0. Okay. And okay, so from 2 to 6, the change of the moment is from 40 to 0. And from 40 to 0, it's steady decrease or gradually or gradual increasing decrease or this one. It only had these three. It only had these three possible situations: steady decrease, or at the beginning it decreases more and the decrease is accelerating after a certain point, or the decrease initially is fast and then gradually decrease the decrease rate is decreased at the end. So there's only three possibility. So let's use the same concept. Because this area is rectangular, so if we slice, we use a dx to slice this area. If you dx to slice this area, we have the same height. So the small area, each small area, the area is the same. So each small area is a constant. That means the moment of change is constant. So that means the slope is constant. So the slope is constant. Only this situation, the slope is constant. Okay, so and here we finish the moment diagram. So here is these two curves is called shear moment diagram of this beam under this external loading and with this A and B support. Okay, that's called shear moment diagram. Okay. Okay, so this is the most simplest example for shear moment diagram. I hope you just practice this. I have lots of example in the PowerPoint. Just practice this and practice in your homework. Yeah, I think you haven't done this before, so you have to get used to this in very short time. Okay, so I won't say it's difficult, but just you have to do some brainstorm. Okay, so bear in mind. So remember this in mind. The moment change equal to area under the shear curve. Okay, and when you draw the shear curve, you only have to consider the reaction force you calculate and the external force in the system. That's it. Okay, it's not that difficult, but it just you have to get used to this. Okay, so this is the simplest example, and later I will show you other more complicated example for shear moment diagram, and talk about something you need to notice when draw the shear moment diagram. Okay, so I'll stop the video here and see you in another video. Bye bye. This one? Oh.